In this example, we'll look at how to find shear and moment envelopes for the factored load distributions on a simple two-span beam that is loaded with both dead and live loads that are uniformly distributed. The magnitude of the dead load is 5 kilonewtons per meter and the magnitude of the live load is 8 kilonewtons per meter, and the span is 5 meters between supports. In doing this, we're going to use the tables for shear and moment coefficients that are found in CSA, in the handbook of concrete construction that is associated with the CSA A23.3 standard. Now, the most accurate way for us to do this would be to develop all the individual factored shear and moment diagrams that are associated with all our different load cases and combinations and with all of our pattern live loading. And then we could plot all of those on the same diagrams and simply find our envelope as the maximum and minimum bounds of those shear and moment diagrams. However, that's not always practical to do. It takes a fair bit of effort, and it's a little bit more convenient for us to have some simple calculation techniques to find the demands upon our structure. So in this case, we'll see that it's not too difficult to do this process. It does require us to keep track of a fair few number of different coefficients and different values. But if we develop a little bit of a system, it's not too bad. We'll also see that in the end, the answer isn't necessarily entirely accurate. We are missing a little bit of information, but generally this is good enough to begin our design. So let's look at what we have here. We have a two-span structure, and it has upon it two different loads. We have our dead load. Our service dead load is equal to 5 kilonewtons per meter. Now, the service load is the magnitude of load that's specified upon the member itself, and this is prior to us factoring it or considering any load combinations or skip pattern live loading. The live load specified over the length of the two spans is 8 kilonewtons per meter. But of course, this isn't the end of the story, because if we go to the National Building Code or to the table within the Concrete Handbook within the A23.3 standard, we see that we need to combine those loads using load combinations. So we can say from our load combinations, we could get load combination 1, which would be our factored load, would be equal to 1.4 times our dead load. And then load combination 2, and let's put A beside it, our factored load would be 1.25 times our dead load plus 1.5 times our live load. And we'll call this load case 2B, would be 0.9 dead load plus 1.5 live load. And all of these are from, we can find this in the National Building Code of Canada or in table C1A of the concrete standard A23.3, which is the front of the handbook, the brown pages within the handbook. Now, if we look at that table, we'll see some other stuff within this. There would be companion loads over here for snow and wind and things like that. And then there would be load combination 3, 4, and 5 that would deal with different principal loads instead of the live load. There would be a principal load for snow, principal load for wind, and then there would be earthquake as well. In this example, we don't have any more loads than live and dead, so we can reduce it to the two different load combinations. When load combination 2 has two different permutations of dead load, either being above 1 or below 1. And the reason for this above 1 or below 1 value for dead load is that sometimes, depending on the complexity of our structure and the relative magnitudes of live load and dead load, we can see that a value of 0.9 dead load would cause higher negative moments in certain regions than 1.25 dead. So until we can rule those out, we have to consider both. Another thing that we need to consider is the patterning of live loads. So this is mandated within the building code. And basically the concept is that if we have live load on structures, this is a variable load. The load's due to furniture and people and things that can come and go within the structure. And there is a pretty good chance over the lifespan of a structure, say 50 odd years, that adjacent spans within the structure will not be uniformly loaded at all given times. So in some times, we might have the full span loaded with live load. So here we would have our factored live load would be 1.5 times WL. That 1.5 comes from these factors over here. However, there are other times when we would only have one of these two spans loaded. And so we would have our live load is 1.5 times our specified value. And in the other case, we might have only the other span load. So this is our adjacent spans loaded or unloaded problem. So now if we look at our problem itself, we have to worry about a few different things. We have to worry about the presence of dead load on the structure, and this would be over the entire span at any given time, and it is either of magnitude 1.4 or 1.25 or 0.9. And when it's 1.25 or 0.9, it is added to the value of live load that's factored by 1.5. However, the value of live load might be over the full spans, both of them, over only one span on the left or over only one span on the right. And we could imagine that as we have more and more spans, there are more permutations of this, and it becomes more and more different cases that we have to study. So we're going to consider each and every one of these. And in this example, I'm going to go through every single different value. However, in practice, once we get into a problem like this, we would be able to quickly rule out some things. Like very soon, I would be able to rule out that load case 2b actually doesn't matter for the work that we're doing. However, I'll follow through with computing it for this whole exercise. I'd also be able to rule out load case 1 from the work we're doing. And that comes from a little bit of experience. But generally, load case 1 will only govern when the dead load is of considerably higher magnitude than the live load. So the dead load and the live load together here do not easily overwhelm the value of the dead load here. So through a little bit of experience or through just working our way through the start of the problem, we could easily identify those cases. However, that's not what we'll do here. Instead, we'll take the path of using the shear or the reaction and the moment coefficients and a little bit of knowledge about how shear and moment diagrams are drawn for uniformly distributed loads to determine the magnitudes of shear and moment at every single point of interest along the length of the span. And once we have those, we can then add terms together, like the value of moment at this point due to dead load, and the value of moment at this point due to live load. And in that case, we might be able to come up with this pattern or that load combination under this pattern of live load. And if we keep doing that for every single point along the span and for every different permutation of live load patterns and of load combinations, then we have thoroughly exhausted all the different possibilities that are out there. So let's begin that process by first looking at what happens to the dead load on the beam. Now, our dead load will always be distributed over the full span of the beam, so both spans, and it's distributed evenly because the beam is prismatic. So here we have our factored dead load. If we look back up at our combinations, we can factor that by 1.4. or factor that by 1.25 or 0.9. And so that's what's going to be happening here in a little table I've built. First, we're going to go through load combination 1 and determine the magnitudes of shear at x is equal to 0, x is equal to 5 meters to the left of that roller, x is equal to 5 meters to the right of the roller, and right at the end of the beam at x equals 10 meters. And from that, we'll have enough information on the magnitudes of the shear from the factored dead load for the 1.4. And then we're going to use a principle of scaling if we find the dead load shear for 1.4 times dead load, and now we want to look at the magnitude of shear for 1.25 times dead load, we can simply scale this one down by the ratio of 1.25 over 1.4. And the same thing will go down with load case 2b, load combination 2b. We'll scale it down from 1.4 to 0.9. Once we have all of those, we'll sort of repeat the process and come up with the magnitudes of shear forces at those locations for the live loads. And then we will simply use superposition when applicable to add the shear force from the dead load to the shear force for the live load and see what the total factored shear force at that location is under our load combination. So to begin this, let's take a quick look at our diagram that's given to us in table 1.15, which is in the white pages of the handbook. So this is immediately after the clauses and the explanatory notes within the brown pages of the handbook. And we have found the type of beam we're working with. And what we see here are coefficients for our reactions that are labeled upon our reactions themselves. And if we take the magnitude of that coefficient multiplied by the load in kilonewtons per meter multiplied by the span in meters, we're going to get a magnitude of reaction here. So thinking through how a shear diagram would look for this particular beam that we have here, our reaction would jump the shear diagram up, and then we would jump up, and then we would follow down with a linear slope until we hit the other reaction. And the slope of that is the magnitude of W. And then we would jump up by a value of reaction here and follow back down and go back up to 0. Now in doing that, we would see that the jump that we took in shear, or the change in shear from this location down to where we are over here, is simply equal to the area under our load curve. So we'll use that knowledge to find the value of shear here, the value of shear here, and the value of shear here. Looking at load combination 1, I am going to take the magnitude of that coefficient at the x equals 0 location, which was 0.375, and I'm going to multiply it by 1.4 W dead. So this is my factored dead load, and multiply that by L. Plugging in some values for that, and I won't plug in values for this whole problem as we go, but I'll do it for some of the time so that we can keep track of what we're seeing here. 1.4 W dead. So this 1.4 W, or I should put in the value for that, pardon me. 1.4 times 5 kilonewtons per meter. So what we have here is the factored dead load for load combination 1. And once again, in case we didn't see it, that 0.375 is coming from this location here. And if we take that 0.375 and multiply it by WL, we get the magnitude of that reaction, which corresponds to the shear at that end. And this all needs to be multiplied by 5 meters. Now, in working our way through this problem, we would be able to look at our unit consistency and see we do get a magnitude of shear after this calculation. And we would end up with 13.125 kilonewtons. So at 5 meters to the left of the support, if we have a known value of shear here, and now we drop down to a value of shear at this location here before we jump up from that reaction point and back down again, the distance from here to here is going to be the magnitude of load multiplied by the length over which load is applied. So we can take the value of shear at x is equal to 0 minus 1.4 WD times 5, or times L. Let's keep variable format. And if we plug in the values for that, we're going to end up with minus 21.875. And moving to the right of this, we're going to take the shear at 5 meters to the left of the support and add to that the reaction coefficient. Let's scroll back up here and take a look at that. The reaction coefficient at this point multiplied by W dead factor times L. So we'll add 1.25, our reaction coefficient, times 1.4 W dead, that's our factored dead load, times L, which will give us the reaction at that point. And we will see now we are at 21.875. Since the beam is symmetric, it's equal span on either side, and the load is consistent and uniformly distributed, we do expect the shear to jump from a negative 21 to a positive 21 because of symmetry of the structure. Now at the end, we can either do the same tactic. We can say that now we're at plus 21.5 and multiply the magnitude of load times the length. So we take 21.5 minus WL and we'll get down to a value here. Or we can take the reaction value, which would jump us back up to 0 shear, and just subtract it from 0. So 0 minus the reaction brings us down to our shear at that location. So that's subtract I'm going to use here. I'm going to take the negative now of the coefficient times 1.4 W dead. This is my factor dead force, dead load, times the span, the single span of the structure. And we'll end up with minus 13.125. Now we see that over here we have plus 13, here we have minus 13, and this works out with what we know about the shear distribution. So we did that work with the factored forces 1.4 WD. Now if we want to go through this and do the same amount of work we can, in fact let me do it for this case here, I'll just switch colors because we're on the next line. Load case 2A has W dead factored is equal to 1.25 WD. And load case 1 was W dead factored is equal to 1.4 WD. So I can very easily just take 13.125 and divide it by 1.4 and multiply it by 1.25, and I get the value of my shear force at that location through a scaling of the shear loads. And since my structure is linear, this is not a problem. Or I can take 0.375 multiplied by 1.25 WD multiplied by L. So here, this is the same sort of calculation we did here. And in fact, we can see that scaling could happen just through the ratio of those two numbers there. And in doing that, I'm going to end up with 11.71875. So over on this side here, at 5 meters to the left, now let's use that scaling factor. So through scaling, I can take 1.25 divided by 1.4. That's the relative magnitudes of these factored loads. And to that, multiply minus 21.875. And I'm going to end up with a magnitude of minus 19.53125. And as I continue this problem, 1.25 over 1.4 times 21.875, I'm left with plus 19.53125, and going to the next part, I have 1.25 by 1.4 times minus 13.125, leaving me with minus 11.71875. So now I am left with my next load combination, and I have load combination 2B. Let's just go back and take a look at what we have here. Here's load combination 2B, and we have 0.9 W dead in this case. So let's go and scale everything by a factor of 0.9 over 1.4. W dead factor is equal to 0.9 WD. So if we take 0.9 over 1.4 multiplied by 13.125, we will end up with a factored dead shear of 8.4375. And continuing that, we'll have minus 14.0625, 14.0625, and minus 8.4375. So these values here came from taking this value multiplied by that ratio. So now at this point, I have enough information to fully describe every single one of my factored dead load distributions for shear. And now what I'm going to do is go and look at what my live load looks like. So here are my different patterns of live load. And here are how I would add those patterns to my dead loads. So in load combination 1, in fact, I've already solved for the complete answer from load combination 1. Here are my factored shears from load combination 1. There's nothing to add to it. Load combination 2A will take the values of my factored dead load shears here and add to it the values of the shear from 1.5 WL. So now I have to consider, what if the WL is distributed over the full two spans, over only the left span, or only the right span? So I'm going to set myself up a little table to consider the magnitudes of shear at those critical locations for each of these three cases. And we'll note that unlike the dead load, where we have different 1.4, 1.25, and 0.9 factors, here all of the load factors are 1.5 for both load combinations, so I don't need to go through that scaling process. So let's go and look at how we compute the magnitudes of that here. And first, I'm going to start with the shear under factored live load for the pattern of loading the full beam with 1.5 WL. And so this would be WL factored. And now below that, I'm going to load just the left-hand span of this with WL factored is equal to 1.5 WL. And then here I'll load the right span of it with WL factored is equal to 1.5 live load. So let's work our way through that. And if we're careful with this, we can very easily see that what we have with this first pattern of loading is simply a scale of what we've been working with dead load. So if we're comfortable with this, we can in fact take this 13.125 and scale it by the relative ratio of 1.5 WL divided by 1.4 WD. That's one way of doing it, but instead let's just go back to the coefficient-based calculations. So we've already seen this shape of it, and we see the coefficients from above, so I'm not going to go back to the table to grab those. Let's grab those coefficients. We have 0.375 multiplied by 1.5 W live multiplied by L. Plugging in all those values, we'd be left with 22.5 kilonewtons. And then through the same math that we did above, through the same rationale, we can take the shear at the left-hand location minus the magnitude of the distributed load multiplied by the span length to get the shear to the left of that roller at 37.5 kilonewtons. And then on the right-hand side of the roller, we have the reaction already contributing. So we're going to take the shear at the left, and to that add 1.25, which is our coefficient from that table above, multiplied onto 1.5 live load times L. And this calculation will leave us with plus 37.5 kilonewtons. And then finally, at 10 meters, we can either continue on and take 37.5 minus 1.25 times, minus 1.5 WL times L. So we can take the magnitude of shear here minus the distributed load to get to the value down there. Or we can simply start at 0 and subtract the reaction. So let's do that. Let's take the reaction away. And we're left with our coefficient with a negative sign now because we're going to subtract it from 0, minus 0.375 multiplied by 1.5 live load multiplied by our span, giving us minus 22.5 kilonewtons. And once again, our knowledge of how this shear diagram should look makes sense. We have plus 22.5, minus 22.5 at either end. And then right in the middle, we have equal but opposite values. And so everything's working out fine for us. Further checks to this, if we wanted to, we could just look at the ratio between this and see if that's the same as the ratio between 1.4 WD and 1.5 WL, since the distribution of load is the same. Now that does not apply to the distribution of load we have here. Now that we changed this distribution, we can expect to see a change in what our shear diagram would look like. In fact, in this case, if I was to draw my shear diagram, I would come up to a value here, And then it would look relatively similar to what we had above, different magnitudes. And then we would come up by a value of the reaction, and we would come across with a straight line and come down. Now, on the other side of that, we would, for the one down below, we would come down and over and up by a value of reaction down to here. So they are sort of mirrored to each other, but they do require us to gather our new coefficients to work with that. So let's scroll way back up here and take a look at our table again. Now we're going to be dealing with this distribution. So we'll deal with that for the left-hand side, and then we'll take that and sort of mirror the values we have. And that mirroring of the values will account for us mirroring the beam itself. So that's load case or load pattern 3. So I'm going to take the 0.438 for the left, 0.625 for the center, and over here we'll note that now this is a downwards reaction, so we'll have to consider our sign carefully when we use that one here. So working through load combination 2, and I'll just switch colors just to keep the numbers from blending together here. We have our coefficient from that table, 0.438, multiplied by our magnitude of our factored live load, multiplied by our span length, and this gives us 26.28. And then we can use the same logic, taking the value of shear at this support minus the area under the load curve will give us the value of shear over here. So we'll come down to this point. We can take shear at 0 minus 1.5 WL, or our live load, multiplied by the live load itself. And this will give us negative 33.72. And then on the other side of this, we can take the shear at 5 meters to the left of the support, and to that we will add the value of our coefficient, 0.625, multiplied by 1.5 live load multiplied by L. And this gives us plus 3.78 kilonewtons. Now we can use the coefficient that we had in the table above, or we can take a look at our knowledge of this shear diagram and say that I expect the shear diagram to look with a flat line without a changing slope from the middle support to the end. And that's because we don't have any distributed load. And that to me means if I know the shear here, I know the shear here. So I can simply write this in as the shear at 10 is equal to the shear at 5 to the right of the support. So this is plus 3.78 kilonewtons. Now, looking at the shapes of these shear diagrams, I suppose I'm going to just delete these diagrams. I'll draw on here after I do it. Well, I'll keep it on. Why not? We have a shear diagram that will look not going well. We have a shear diagram that will look like this over here. And if we want to look at the shear diagram for the one below it, we would say that this reaction down here will jump it back up to 0. And so we sort of have a somewhat inverted and mirrored diagram for the one below it. But the magnitudes everywhere are going to be the same. The magnitude of shear at this point corresponds to the magnitude of shear here. The magnitude of shear at this point corresponds to this point here. This point corresponds to there, and this point to here with opposite signs. So knowing that, I can go and write in those values. Minus 3.78, minus 3.78, plus 33.72, and minus 26.28. So now, at this point, I have completed all of the work I need to do to find the shear force envelope for this problem. Looking back at what I've done here, I have found my load combinations. And now for load combination 1, I've found the complete shear diagram for that. for load combination 2A, I've found the shear diagram here, and I've found the shear diagram for 1.5 WL under scenario 1, 2, and 3. So now if I take those individual scenarios and add them to here, I would have 3 different shear diagrams. But I'm not going to do that. Instead, I'm going to look for worst case scenarios that come out of here and add it to worst case scenarios that come out of these ones here. So what I mean by that is that if I look at location X is equal to 0, and I have 3 different load combinations, load combination 1 can't add any live load to it. So load combination 1, the shear is 13.125. And is that a relative and absolute maximum or value? Well, the answer is no, because if I go to load combination 2A, I'm going to take the value of shear from 1.25 W dead and add it to the value of shear from one of the pattern live loadings that has already been factored by 1.5 WL. So in fact, if I look carefully at this, the biggest value that I could come up with would be 26.28 plus 11.718. Other combinations would be 26.28 plus 8.4375, or minus 378 plus 8.4375, or minus 3.78 plus 11.71875, or 22.5 plus these values as well. So the biggest of them is going to be this and this one together. So now below, I'm going to write that out. Let's circle them here too. Here's the biggest one for that, and that's going to be added to that. So the load combination that I'm adding in is load combination 2A, and the distribution of load that caused this shear to be, or live load that caused me to select that, would be live load pattern with the load only on the left hand side. And plugging in the values of shear that I found, I have 11.71875 from my dead load factored and 26.28 from my live load factored, giving me a total value of 38 kilonewtons at X equals 0. Now at 5 meters to the left of the support right here, I can go through the same work, and it's either going to be minus 21.875, or it's going to be the sum of this plus one of these 3, or this plus one of these 3. And here we're looking for the biggest negative number, and it's pretty easy for us to say that once again, this 19.5 from load combination 2A will be added to one of our live load patterns. And in this case, we're going to choose the value from our full distribution of loading. So I'll plug that in here, and I have still the load combination 2A, but now my pattern live loading is over the full span, or over both full spans. And plugging in the values I have for that, I have 19.53125 and minus 37.5. Adding them together, I have minus 57.03 kilonewtons. Going through the same thing at the right location, I would see that I have the same problem, and I can add the same 2 locations together, and I'm left with load combination 2A and full distribution of load over the spans, and plus 19.53125 and plus 37.5, giving me plus 57.03 kilonewtons. And then finally, on my other span over on the right, I'm going to look at this, and I'm going to say that once again, load combination 2A is going to govern when I add it to the value of minus 26.28 from the pattern live load distribution with the load all over on the right-hand span. And again, my other options would be this value on its own, 1.4 WD, or this value for load combination 2A, plus any of these that would give me the biggest absolute value for shear, or this value for load combination 2B, plus any of these. So the biggest absolute value comes from the sum of 26.28 and 11.718. Adding those together or filling in my table, I still have load combination 2A, and now I'm dealing with all the load over here, and adding it all up, I have minus 11.71875, minus 26.28, so for a total value of minus 38 kilonewtons. So this is enough information for me to now draw my factored shear envelope diagram. And I'm going to draw this out and then just talk briefly about it before we move on to the moment diagram. I've already given myself a few points to work with here, so I'm going to just draw this in. The slope of this curve is going to be equal to, so the slope here, the slope is equal to W factored. And that's the value of W factored that we used to get the magnitude of shear at this location. And we'll note that what I end up drawing here, the shear shear envelope is not, well, let me draw what it's not first off. Let me draw, well, no, I'll draw what it is, and then I'll draw what it's not. That's an easy way to do it. So, we look at our shear envelope. We'd have something that would look like this. And let me put in some values, and then I'll talk about this and show you what it isn't. 57.03, minus 57.03, minus 38, and plus 38. So drawing this is somewhat qualitative because I don't yet know where these dimensions are. Here would be a question mark. So to find this, we would need to compute them from the WF values. So we could take the factored load that got us this point in the shear diagram and say, what is the X value multiplied by WF that would be equal to minus 57.03? So here, let me just write that in. X WF is equal to minus 57.3 for this location. And so this would be the magnitude of the distance between the two is X from over here right across to over here. And so all I'm saying there is what is the length I need to have a continuous distribution of load to make that happen. And since if I look at this, if we can see quite easily that here WF would be the slope of the line. Now, I was going to say what this shear diagram is not, let's draw this in green. I found the maximum values at each point. It is not simply a straight line connecting the two. That's because one of these combinations up here came from us using 2A, whereas this line down here came from us using, or not 2A, using this live load pattern for this one, and this live load pattern for this one. So there's a little bit of an offset because of that. This may or may not be important to design, but generally by using a method using these coefficients, we accept that we don't know everything about this, and if we do need to compute that X value, we'll go through the extra amount of work to do it. But often this magnitude and this magnitude here would be what we'd be looking at for design alone. Now another thing that we could say is technically shear doesn't matter whether it's positive or negative in terms of how I resist it in the beam itself. So really I could draw my shear diagram as my shear envelope as this here, where I cut out the little tails of this because the relative values here is bigger than the value here. So this doesn't matter because it takes over down here. But that's a little bit of extra nuance that we don't necessarily have to go through in this work. Instead, we sort of sketch what we think it looks like qualitatively. Let's just replace that sketch and then move on to our moment distribution. So moment is actually going to be easier for us to find than shear, and that's because there's coefficients for a moment that are directly given to us rather than coefficients for reaction. But we're going to go through exactly the same process. However, before we do that, we know that at the terminal ends of this continuous beam, where there's a pin and a roller, of course our moment has to go to 0. So if our moment goes to 0 at those locations, under any possible distribution of loads, it doesn't matter what we have there, then there's no need for us to go to the work of calculating that. Instead, what we're going to compute is what is the moment in the middle of each span, and what's the moment at the interior support locations. And we'll see that those values correspond well with what is given to us in these coefficients. Here we have the moment at the interior support. Here we have the moment coefficient at the middle of the span. And by symmetry, we have to recognize that that's the same value as what's going to be over here. And then over here, we have a moment in the middle of the span and a moment at the supports. And I'll talk a bit later about what the moment is there. When we compute moment, we simply take the coefficient that's written there horizontally, multiplied by the magnitude of load times the span squared. And once again, we'll look at the unit consistency of that when we do our first calculation. So I'm going to pull this minus 0.125 and the 0.70 or 0.070 out for now. And we'll go and look at what are the moments due to dead load. Moments under factor dead load. So once again, I have dead load will always span the full beam. So this is W dead factored. And at x is equal to, here is x, at x equals 2.5, which is right in the middle of the span, I am going to have the coefficient 0.070 multiplied by W dead factored multiplied by L squared. And so plugging in some values for that, under load combination 1, W dead factored is equal to 1.4 W dead, I'm going to get 0.070 times 1.4 times W dead, which is 5 kilonewtons per meter, times 5 meters squared. And looking at the way that the units work here, I'm going to lose the meters on the denominator and one of these meters here, so I'm left with kilonewton meters. And this would be 12.5 kilonewton meters. At 5 meters, I have a coefficient of minus 0.125, so this is my coefficient, multiplied by W dead factored, multiplied by L squared. And going through the same calculation, I would have minus 21.875. And over on the right-hand side, at 7.5 meters, which is right in the middle of the span over here, I have the same thing as at 2.5 meters, 0.070 W dead factored times length squared. And I'm left with plus 12.5 kilonewton meters. And of course, once again, at the very ends, we're left with 0. Now if I look at load combination 2A, I have W dead factored is equal to 1.25 W dead, and like what we did before, load combination 2B, W dead factored is equal to 0.9 W dead. So I'm going to just go through and multiply the ratios through this. I have 1.25 over 1.4 times 12.5, and I'm left with 11.1607 And over here I have the same ratio, 1.25 by 1.4 times minus 21.875. And I'm left with minus 19.5315. And then 11.1607. Moving down to the next combination, 2b, I have 0.9 over 1.4 times 12.5, and this gives me 8.0357 minus 14.0625 plus 8.0357. So then I'm going to go and do the same thing as I did for shear under the different patterns of live loading, and I have the combination 2A and 2B both factoring the live load by 1.5. So here this would be 1.5 WL is equal to WLF, factored live load. And then the next one over here, I would be loading the left-hand span with 1.5 WL and the right-hand span with the same thing. And we'll be looking for the moments at those same locations, 2.5, 5, and 7.5. So middle of the span and at the support locations. The distribution of load for this first pattern is the same as for the dead load, so we won't need to go back and look at that table. We can just pull these factors out here. Or we could take that 12.5 and scale it by the magnitude of WLF divided by WDF. But instead, we'll go through the coefficient term. 0.070 multiplied by WL factored multiplied by L squared. Or 0.070 multiplied by 1.5 times 8 kilonewtons per meter multiplied by 5 meters, all squared, giving me 21 kilonewton meters. And I'll do that scaling over on this one here. So now what I'm going to do is I'm going to scale, using this value, I'm going to scale by the ratio of W live to W dead. So WLF over W dead factored times the value of minus 21.875 would give me minus 37.5. So in case I lost anybody there, I could go through this same equation and substitute this for WLF, or I can take the ratio and multiply it by that value and get the same answer because the distribution is the same. And over here, once again, what I gained in knowledge over here, saying since I have symmetry, this moment here has to be equal to the moment over here. So this moment here is equal to this moment here. So the moment at 2.5 is equal to the moment at 7.5. Moment of 7.5 meters is equal to moment 2.5 meters, giving me 21 kilonewton meters. Well, I only have 2 more to go. So let's look at this one here. I'm going to go up to that table again, take a look at it. So the moment coefficients given here and here. Let me draw the moment diagram before we continue. And I'm going to be using the moment diagram convention for reinforced concrete, which would be to draw the positive on the bottom and negative on the top. So in doing so, I would end up with a moment diagram for this problem that's going to look like that. I have over here a parabola, and I know that to be a parabola because I have a UDL, which causes a linear shear diagram, and a parabolic moment diagram. Over here I have no load, which causes a constant shear diagram, and a linear moment diagram. So now, if I am interested in the magnitude of moment right here, if I take moment, let's call that moment 1, I would say that moment 2 is going to be equal to moment 1 over 2. So this table requires us to have a little bit of knowledge in that to be able to find interior moments in cases of unloaded spans. This isn't the problem we're doing, but here's another example for 4 equal spans. Here's an unloaded span where we'd have to find the values of moment at those locations. And here we would have a moment diagram that would come up to a negative moment. It would come across straight and, well, it would come up to a negative moment. It would come on some sort of line to another negative moment, and it would keep doing that. So if we wanted the moment in the middle, we'd have to take the average of this one and this one to get it. So I'm going to use that principle down below. I'll take that minus 0.063 and the plus 0.96 down below. 0.096. So I have 0.096 times our live load factored times L squared. And plugging in all those values, I have 28.8 kilonewton meters. And at x equals to 5 meters, I've got minus 0.063 multiplied by live load factored multiplied by L squared, giving me minus 18.9. And over here, from the discussion I just had, let's just zoom in and I'll resketch it here. I've got a beam that is supported there, supported there, supported there. My moment distribution is going to look something like, well, let's use the line to clear it up here, something like that. So here, if this moment here, this moment is 18.9 with the minus sign. This moment here is going to be minus 18.9 divided by 2. So the moment at 7.5 is going to be equal to minus 9.45 kilonewton meters. Oops. Now, I'm going to take a shortcut here. Not really a shortcut. Once again, we're relying on the knowledge of the moment diagram shape to do these problems. So this is my moment diagram shape over here. And well, let's even sketch that in. This is my moment diagram shape here. And this is my moment diagram shape here. And we'll see that they are mirror images of each other. And so I don't need to do any calculations. I can simply take the values that I found at 7.5 and move it to 2.5. So I can take this and call this minus 9.45 minus 18.9 and plus 28.8 kilonewton meters. And we are very nearly done. So now we have to add them together according to our load combination. I'm going to rewrite the load combinations, or we can see it here, and say that we have load combination 1 is equal to 1.4 W dead, would be our factored load. And load combination 2, A, would be 1.25 W dead plus 1.5 W live. And load combination 2B is 0.9 W dead plus 1.5 W live, giving me that. So now, having established those, what I'm looking for is what will give me the biggest positive and negative values at these locations. And so first, let's look at load combination 1, which is just here. And I can say at x equals 2.5, I have 12.5. But a quick look at any of these other load combinations where I add 1.5 WL, I've got 21 and 28. So this one won't govern. And over here I've got minus 28. Well, here's minus 37.5. So there's no way this will govern, and the same thing over here. Load combination 1 won't matter. And in fact, I can go through here and I can pick the things that add to the highest value. So here I've got 11.1607 plus 28.8. And so here I'm using load combination 2A, 1.25 W dead plus 1.5 WL, where I have only the left-hand span loaded. And in the middle of the beam, at x is equal to 5 meters, I'm going to end up taking the same load combination 2A, but now I'm going to add to it 37.5 that is from both spans equally loaded. And over here, I can take that same value here and add to it now 28.8 from the right-hand span load. So let's put that in our table down below and finish this problem off. We've got load combination 2A for all of these again. And you can see that although we computed all the numbers here, it wouldn't take us too much practice at these sorts of problems before we could quickly rule out load combination 1 from mattering, and we wouldn't have to follow through with that as much. And load combination 2B, we could rule out in certain cases pretty quickly as well, just by exploring the magnitudes of coefficients before we do all these calculations. So let's plug in the live load patterns that govern for these. And here I've got this pattern here. Here I've got the pattern that governs both spans, and over here is the right-hand span. Writing out the moments, 11.1607 from dead, 28.8 from live, giving me a total moment of 39.96 kilonewton meters. And over here I have minus 19.53125 and minus 37.5, giving me a total moment of minus 57.03. Over here, 11.1607, 28.8, and 39.96. These values here are our design moments. Let's go down to our moment diagram and see what this might look like. So over here I've got 57.03 negative drawn on the top. At 2.5 I've got 39.96, and over at 7.5 is 39.96. I go to 0 at the very ends, and I know that my moment distribution is parabolic. Now, another thing that I'm going to have to look at for this, let's draw what the moment distribution looks like. And this is the same discussion that we've had for the shear distribution. I've got a parabola for the positive moment. I've got a parabola for both positive and negative, actually. So that should be a nice straight line, but I have a hard time with this pen, or a nice smooth line, but this digital tablet gives me a bit of an issue to do these sometimes. Let me actually redraw this one here a little bit better. Yeah, I can do that here. That was a pretty good one. All right, and then over here, my moment distribution is going to look like that. So if I was to carry these over, I'm not going to do it here, from my individual loads, this would be my distribution of moment for load combination 2A uniformly distributed. It would come across here and here. But this one takes over because it's a higher magnitude of moment. So the next thing that I have to look at is the locations of my transitions from positive to negative moment. Here and here. And let's measure from here over to here. Now these locations I'm not going to compute in this example, but like we discussed with the shear force one here, if we wanted to figure out what we've got at those two locations, we would have to go back to some equations for a moment. So to find these, we would need to look at actual moment distribution equations. Which can be a little bit of a challenge, but it's not too bad. We just have to identify what load combination does this thing act upon. And then from that, we would then develop an equation for this. Now, one thing that I would point out at this stage is that if I was to carry this over to there, I could figure some stuff out from this pretty easily, because what I have is the shape that I'm about to shade in here is equal to a shape here where this is a simple supported beam under uniformly distributed load with the addition of, so a simply supported beam under uniformly distributed load with the addition of an end moment M. And this would leave us with a moment diagram that would look like this on that beam. So we can go and we can find some equations for some parabolas that have been added to a line and get those quite simply. However, it does become more and more onerous to find all the values from this sorts of method if we want them. And at a certain point, the utility of using the coefficients method is lost, and we should go back to full equations, as I discussed at the start of this example, where we would plot all the different moment diagrams on top of each other. Another thing of note, and it's probably not all that important, but in fact, this is the location of the maximum positive moment. Because in a parabola that has now been rotated, it is no longer at the maximum at our zero location. And so at this point, it's important for us to identify we've got positive and negative. So the length over which we've got negative moment up here is going to be the length over which we need to reinforce the top of a concrete beam. And the length over which we have positive moment is going to be the length over which we need to reinforce the bottom of the concrete beam. And this is why we go through the effort of drawing the moment distribution for our moment envelope, is that now we can cover all the different scenarios of loading in one diagram and tell us all the locations where we need to place our reinforcement with a simple graphical tool that we've just developed. But that will come later as we move on in reinforced concrete course. We'll learn how to distribute that reinforcement in order to resist these moments.